Well, welcome everybody. Thanks for attending our webinar at the end of a long year, which was full of challenges. And no doubt we're all looking forward to the summer break ahead. My name is Stephen Gamble. I'm the team leader for Applied Maths and a few other subjects as well. And I just want to say a few words before I hand you over to Brendan, Owen and Angela for the remainder of the webinar. So we're in the last days of the old applied maths syllabus, and Friday, the 24th of June, will officially mark its retirement with the last group of students due to sit an exam based on it. And our new specification builds on a lot of good learning contained in the original syllabus to include some new topics such as networks and graphs, but also places an emphasis on the skills required by an applied mathematician. These skills are described by the unifying strand of mathematical modeling and include the ability to formulate a problem, translate a problem into mathematics, compute solutions, and evaluate solutions. And these applied math specific skills sit within the wider framework of senior cycle skills and the ability of students to communicate effectively, be personally effective, work with others, think critically and creatively, and to process information. And I want to chat about these because they're not easy skills to develop, and many of you have probably seen this for yourself in the year gone by. But they are important because these skills will be assessed in the Leaving Cert Applied Maths exam in June of 2023, and also through the Leaving Cert project work, which your students will engage with when they return to school in September. And so the development of these key skills by us and our students in our applied maths classrooms are critical to student success in the Leaving Cert. But they're also important if we take a longer term view because they're the skills needed by practicing applied mathematicians. And no doubt all of us on here this evening have an interest in promoting our subject, and applied mathematicians have a particular set of skills which can contribute a lot to the world today, and we've seen the influence of modelers on the world around us, particularly over the past 2 years, and the importance of having those skills within our society. As I mentioned at the start, it's been a challenging year in schools, and I want to commend all of you for engaging with the new specification and with the professional development provided by Brendan, Owen, Angela, and our wider team of associates. We know it hasn't been easy to be away from your students at any stage, and we appreciate the efforts made by everyone to engage with us. And the PDST Applied Maths team believe it's important that the support we provide to you reflects the commitment you show to the subject and to your students. And following on from my email a number of weeks past, I want to reiterate the importance of teachers attending and engaging with the seminars, PLCs and webinars that we put on, because this helps us to continue to make the case for providing quality support to you. So before I hand over to the team, I just want to finish by saying something about the applied maths community, which is made up mainly of teachers such as ourselves and yourselves, but also our colleagues in the NCCA, the Inspectorate, the State Exams Commission, the IAMTA, and at third level. And I have to say, it's been a great community to work with over the past 18 months as we've rolled out support for the new specification. There's a real sense of everyone pulling in the same direction and trying to do the best for the subject and for the students. We've come a long way over the past 12 months in terms of our understanding of the specification, and there's no doubt we have a way still to go yet. And next year is likely to present us with a number of new challenges, particularly as the pressure of projects and exams start to rear their heads. But we'll work through this too, and we'll do it in the way that we've done all of this so far, and that is together, and our students and the subject will be all the better for it. So thanks again for everything that you've done over the course of this year. I wish you the very best for this webinar, for your summer break, and look forward to seeing you all again in September. Brendan.
Thanks, Stephen. This seminar will last about 45 minutes, and we hope that by the end of the seminar, teachers will have experienced how project scheduling can be developed and formalized through authentic modeling problems, experience Bellman's principle of optimality and its appropriateness through the lens of mathematical modelling, and be more familiar with the growing bank of resources available to teachers of applied maths. So let's get started with our first task, that of examining project scheduling and critical path analysis. We'd like to direct your attention to the specification. To recap on the purpose and content of each of the 4 strands of learning, but specifically to impress upon you, the teachers, the importance of the unifying strand. The new specification is made up of 4 strands. In strand 2, students learn about networks and graphs and how they can be used to solve real-world problems, such as calculating the shortest or quickest route in a journey, which is the basis of Google Maps. They'll encounter content such as matrices and various exciting algorithms, 2 of which will be addressed in this webinar. Strand 3 explores the motion of an object. It involves analysing speed, acceleration, forces, vectors, and collision of objects. Strand 4 will investigate areas such as difference and differential equations and how they may be used to model population growth, predict changes in the economy, and even calculate the terminal velocity of falling objects. Strand 1 is the unifying strand where students learn about mathematical modelling as a process in solving problems. So a question we may ask ourselves is, what does maths modelling mean to us as teachers? And how do we reflect this understanding in our classroom? But for the purpose of this webinar, we'll focus on strand 2, algorithms. Our students, you'll see, should be able to apply network concepts to project scheduling and apply the concepts of critical path, early times, late times, and floats to project scheduling. So you might ask, what exactly is project scheduling and why should we use it? It involves planning the order of activities in any kind of a project. It could be a project in the business world or a student's Leaving Cert project. Some activities might depend on the completion of others, such as in the construction industry. From our example listed, we understand that when building a house, the builder can only complete certain activities or jobs once other activities are complete. So why use it? It allows people the opportunity to estimate the total duration of a project and when to do certain activities. It allows users to identify which activities must be kept on track time-wise and which could be delayed without affecting the total duration of the project. Ultimately, project scheduling determines the shortest possible time to complete a project. So where do we get to use it? Critical path analysis is a widely used project management tool. The advantages to efficient project management will vary from industry to industry, but in general, having a more accurate idea of how long a project will take will help with business planning, budget estimates, staff, or raw material requirements. We have an example there. If a company can predict whether or not its new toy will be developed in time for the busy Christmas shopping period, it is useful as that could have a major impact on sales and therefore company profit. Critical path analysis applies to everyday activities too, like preparing for or planning a trip abroad. We're all familiar with our checklists, ensuring everything is ticked off, always in a logical manner. When cooking breakfast, we wouldn't cook each item separately. Some items may cook simultaneously, while some items or activities might be delayed without affecting the overall serving time. So we might pose the following problem to students. How quickly can they prepare tea for 4 guests? We want students to consider the question first by themselves. This is part of the process of learning to be a modeler. To take a poorly defined question, drill down into it in order to understand it, and then redefine it mathematically, making a number of assumptions. As teachers, we will always encourage our students to refer to the modeling cycle, formulating the problem, redefining it mathematically, calculating a solution, analyzing the solution, then deciding how they might best refine it to make the solution more accurate. This may then lead to a discussion in class in which the following 10 individual activities may be highlighted as necessary for the timely completion of the project. However, the students would have to agree on the order of the tasks. We might also ask them to estimate the time taken to prepare tea for these 4 guests. This could be very useful when analysing the final solution later on. When the students have indicated that they have some idea of the order of tasks, we introduce the notion that certain activities have to take place before other activities take place, thereby introducing the idea of precedence. And now that we've decided the order of activities of making 4 cups of tea in this particular case and discussed the concept of precedence, we'd ask our students to put these activities in the order, in the correct order, in our given precedence table. The list of activities and their associated times from the first table are transcribed to the precedence table. The first activity is placed in the first row, followed by the next activity in the next row, and so on. The predecessor column outlines which activity must have taken place before the given activity can happen. In our next image, the complete precedence table will appear. We now see the completed precedence table. Now we'll see, can we represent this as a network graph? We can see that activities E and F have no predecessor. So we start our graph with both E and F connected from the start. Next, we see activity I follows activity E. As E is its predecessor, so we show a connection from E to I. Similarly, activity B has as its predecessor E, so we show a connection from E to B also. Activity J has 2 predecessors, I and B. So we take an arrow from I and an arrow from B, both leading to J. Activity D follows activity J. J is its predecessor, so we connect an arrow from J to D. Our next activity on the precedence table is interesting. It's activity G. This has F as its predecessor. So before we connect an arrow from F to G, we look forward and we see that both G and D are predecessors for the next activity A. So when we're drawing our arrow here now from F to G, we'll make sure it's long enough to make the next activity easier to read. As mentioned, both G and D are predecessors for the next activity A. So we connect an arrow from D to A and from G to A. There are just 2 activities remaining. Activity H has A as a predecessor, so we connect an arrow from A to H. And our last activity C has activity H as a predecessor, so we connect an arrow from H to C. As this is our last activity in the precedence table, we close the graph with an arrow from C to the finish. So now we're in a position to determine the critical path. And the critical path for this schedule of activities as represented in both the precedence table and its corresponding network graph will develop it. While discussing this concept in class, students might develop a shared understanding on what a critical activity is. A critical activity, it's an activity to provide services in which a disruption of display will have significant impact or influence on the schedule. We'll keep a table of the activities at the end of the screen from this point on, just to remind us what each activity represents. So we're going to apply a rough grid for each activity. The grid will be made up of 2 rows and 3 columns, and we'll place one at each activity. We see in the central column, the central 2 boxes, that represent the activity and its duration beneath it. From the image at the top right of your screen, we identify the contents of 2 other boxes, and we'll develop meaning and understanding of all of the boxes in the grid as we progress through this problem. We've already identified 2 central components of the 6-box grid, that of activity and duration. So we direct your attention to the top left and top right of that grid. We'll have start and finish. So the start time plus the duration would be equal to the finish time. Let's look back at our graph now. We can see from the graph that both E and F can start the process and they're independent of each other. So let's indicate their start time as 0. And how long before E and F are finished? In class, we would seek verbal solutions from our students. And they could say that activity E starts at 0 minutes, its duration is a ½ minute, so it'll finish at a ½ minute. Activity F starts at 0 minutes, its duration is 1, so it should finish at 1. We can now see that both I and B can only commence once E is finished. So again, we would ask in class, at what time can we start I and B? As both activities can only commence when E is complete, our students will understand that both I and B have a start time of a half. Our students might then suggest the finish times are 3/4 for I and 3½ for B. This brings us to activity J. J can only occur when I and B are complete. So we would hope that our students would choose the larger of the 2 values. Why? If they chose 3/4 of a minute, clearly B wouldn't be complete. By choosing 3½ minutes, both activities are complete. If we go to G, we'll see G can only commence once F is complete. So it'll commence at 1 and finish at 1½ As we mentioned, J would be commencing at 3½, so its finish time would be 4. At this stage, we'd take a rest. We'd ask our class to complete the graph as best as they can, offering guidance as they progress if they need it. And for the rest of this slide, I'll continue with the anticipated response of students to complete the grids. We can see here that D follows J. So D will only start once J is complete. So D will start at 4, and 4 and 2, it'll finish at 6. Now we have a decision. What happens at A? What's the earliest it can commence? We'd ask our students to verbally reason their solutions. Activity A. Well, it can only commence once D and G are complete. So we would hope that they'll go for the larger of the 2 values. And from here on in, the rest of the graph should be plain sailing. A starts at 6 with the duration of 1, will finish at 7. H will start 7 minutes with the duration of 1 and finish at 8. And C will start at 8 minutes with a duration of 5, finishing at 13 minutes. In conclusion, we've determined that moving forward through the activity list will, from the beginning to end, will take 13 minutes. This is referred to as a forward pass for a scheduling network in our specification. But we might ask, have we any wriggle room with these individual activities? We've started each activity at its earliest possible value, but can some of them start later than mentioned and still not affect the finish time of 13 minutes? Or are there some tasks so tight for time that by delaying them would result in delaying the complete schedule? We really want to see if we can delay the start of a process and thereby delay its finish time without affecting the overall scheduled time. So we're going to redefine our grid. And our value there, start in the first column, is going to be redefined as early start and late start. Sorry for that, folks. And our finish column will be redefined as early finish and late finish. Mathematically, late start plus the duration is equal to late finish time. So if we have any two of these three entries, we can find the third. If we have the late start, duration, we could find the late finish. Any two of these will find our third one. So now we look at our grid. And on our grid here, we check the end row in each case. And we see the only row that has two entries will be the last row, that for activity C. So with that, we said that the latest C could finish, and be no later, would be 13 minutes. So we can now determine the 13 minus 5. We can determine the latest that C can start. But C can only start once H is finished. So the latest H can finish would have to be 8 also. And 8 minus 1 would mean that H, its latest start time would be 7. H can only start once A is complete, once that's finished. So A would have a finish time of 7, bringing back to saying that A would have its latest start as 6 minutes. Now we come to a junction, and at this stage, we come to a decision. What's going to happen? The latest start for A is 6, and we're wondering what's the latest that D and G can finish. So in each of their cases, it would make sense if they both finished. The latest they both finished was 6. It could be no later than that. This would lead to a start time for D of 4 and a start time for G of 6 minus a half is 5.5. Now, if we look at J, again, D has a late start of 4, which means J would have to have a late finish of 4, working backwards would be 3.5 for the late start. And from J, we have another junction, another decision. What happens? What's the latest finish for both I and B? Well, if the latest start for J is 3.5, we would hope our students would suggest that the latest finish for both of these would also be 3.5. Our students can again nominate the answers as a quarter minus 3.5 minus a quarter is 3.25, and 3.5 minus 3 is a half. Before we get to E up here, we'll follow along this line down here from G to F. So we said that G had a late start of 5.5, which means that F can finish no later than 5.5, which gives it start time of 4.5. And now we're back up to probably the biggest decision of this graph. What will be the latest finish for E? Will it be 3.25? Will it be a half? We could seek verbal solutions from our students, and in that response, students may determine that this process is actually the reverse of the earlier forward pass method, and for that reason, they're going to select the smaller of these two values. And that would be a sensible approach. But it begs the question, what if they chose the larger one? And if they'd chosen the larger value and put 3.25 here as the latest finish for E, and if they were to work forward again, the knock-on effect would be B would be 2.75 minutes longer. And at the end of the day, when we go through it all here, C would finish at 15.75 minutes, which wouldn't be acceptable because we're not allowed to finish any later than 13 minutes. Our purpose is not to delay the finished project time, but to see where some flexibility may exist in delaying tests without delaying the overall project. So then if we just finish this chart here, half minus half, we're back to 0. And now we're in a position that now we can actually, we're ready to identify critical activities and the critical path. This has been referred to as a backward pass. Having completed our forward pass and our backward pass, we can now identify our critical path. Our critical path involves all of the critical activities, which are activities that cannot be delayed, or else the total duration of the project will be delayed. So we display our work to date, and we pose the question: how might the difference between the late finish and the early finish help us to identify critical activities? Well, this difference between the late finish and the early finish is actually referred to as a float. So if we do that calculation, we do late finish minus the early finish, 0, 5.5 minus 1 is 4.5, and let's fill it in. And we see there's absolutely no wriggle room for some activities. Our students might anticipate how these values may help to identify critical activities. So an activity is said to be a critical activity if its float is 0. So floats of 0, E, B, J, D, A, H, and C. Let's light them up. And they're the critical activities. So the critical path will be from start to E, B, J, D, A, H, and C. And this was determined by calculating the float, which was the difference in the late finish and the early finish. Would it be the same if we got the difference in the late start and the early start? It's a question we could pose to our students. And in fact, you can see that it certainly will be. If we look at F, 4.5 minus 0 is 4.5. All the others are consistent up there. And down here, 5.5 minus 1 is 4.5. Yes, it is. Now let's interpret the solution. We have the solution there, and we have our list of activities beneath it. Our question might be, how do we interpret the non-critical activities F, G, and I? We'll consider in this webinar 2 of these activities, F and G, and I'll allow you to consider activity I on your own. Activity F has an early start of 0 minutes and a late start of 4.5 minutes. So we can delay by F by 4.5 minutes without affecting the overall schedule. If we look at G, G has also an early start of 1 minute and a late start of 5.5 minutes. So it can also be delayed by 4.5 minutes. Questions our students might ask is, does this mean we can delay each of them by 4.5 minutes, making a total of a 9-minute delay? No. Between them, they can delay as much as they desire, as long as G here has a latest finish of 6 minutes and no more than that. This brings the problem on critical path analysis to an end. It's important that the student is aware of the mathematical modeling cycle and the fact that they have formulated the problem, mathematized the problem, and have now assessed their solution. If they're to continue with this as an authentic real-world modeling problem, they should consider how they might reiterate the solution. With that, pass you over to Owen.
Smashing. Thanks very much, Brendan. So what we'll take a look at now is we're now just going to take a look at the area of dynamic programming and Bellman's principle of optimality. Smashing. So, the dynamic programming and Bellman's principle of optimality is our 4th algorithm in strand 2. And what it does is it focuses on the optimal side of decision making. So here's a section from the specification regarding Bellman's principle of optimality. We can see here on the left that students will learn about dynamic programming and shortest paths as applied to multi-stage authentic problems such as stock control, routing problems, allocation of resources, etc. In the right-hand section, we see that students should be able to use and apply dynamic programming terminology, which we'll take a look at in a moment, apply Bellman's principle of optimality to find the shortest paths in a weighted, directed, acyclic network, apply Dijkstra's algorithm to find the shortest path in a weighted, undirected, and directed network, and finally, evaluate different techniques for solving shortest route problems So it is important that students have an understanding regarding the appropriateness of each. So what is Bellman's principle of optimality? It's a technique for solving multi-stage decision-making problems. The goal of these is to optimize time, profit, or resources. In National Seminar 5, we developed this algorithm in an alternative way to how we'll approach it today. And in Seminar 5, we used a concepts through modeling approach that led with a modeling problem and built the learning of new mathematics around it to develop both mathematical and modeling skills. The principle itself states that any part of the shortest or longest path between the source, which is the start, and the sink, which is the destination, is itself a shortest or longest path. Or put more simply, any part of the optimal path is itself optimal. So, for example, you can see from the map on the right that the shortest path from Cork to Galway is the path Cork to Mallow to Charleville to Limerick to Galway. So the shortest path from Mallow to Galway then is to go from Mallow to Charleville, Limerick to Galway, which is part of the larger optimal path. Let's now take a look at the terminology involved. The specification says shortest paths as applied to multi-stage problems. A multi-stage graph is a directed graph in which all vertices or nodes can be divided into a set of stages such that all edges are directed from one stage to the next stage only. A state then is the vertex being considered at each point. This is the point where we make our decision regarding the optimal choice. A stage is a collection of directed edges or moves and represents the transition from one set of states to the next. Stages could represent time intervals or the phases of a project. Finally then, an action is a directed edge from one state to the next. This could be deciding to use one product over another or to invest or not invest. So let's apply all of that to a problem. A company that owns an apartment building is planning upgrades and regular maintenance for the building over the next 4 years. They hire a project management company to plan the work needed and research the costs involved. Horgan Project Management investigate the possible costs involved for works such as painting, upgrading the heating system, better insulation, anything that might go with the upgrading or maintenance of a large building. They also have to make some assumptions as they plan when to do the work over the next 4 years. For the first iteration, they will initially assume that the same services at the same cost will be available for the first year and the subsequent years after that. This could be refined in further iterations to improve their model. These are all skills that are part of formulating any problem where students have to research the background to a problem, determine information relevant to it, and determine what assumptions are necessary to simplify the problem situation. So these are all really important skills for students engaging in any form of a mathematical modeling problem. Then the maintenance company took all of the gathered costs and information and translated them into a mathematical representation. The network on the next slide represents the decisions associated with the upgrades and maintenance of the building over 4 years, and the company wished to minimize their costs. Our goal is to determine the decisions that the company should make at different points over the 4 years in order to minimize the costs and also calculate the average yearly cost based on those decisions. So here's our network. And this network represents the various options for upgrades and maintenance each year. The weights on each edge or action represent the cost in thousands of euros of various upgrades that were mentioned earlier, like the upgrading of the heating system, painting, insulation, etc. Our goal is to apply Bellman's principle of optimality to the given weighted network and find the minimum cost for the 4-year period. So we'll now apply Bellman's principle of optimality to the network by working our way through the stages and making the optimal decision at each state to minimize our cost. Since this is a directed multi-stage graph, then we will use a technique called backwards induction, which starts at the end and works backwards. It reduces the number of routes that must be explored, because if we start at t, then the value of t to itself is 0, and then we move back and examine g and h. At g and h, there is only one action that will get us to t, so the optimal decision is simple, and we build on those decisions, moving backwards through the stages. While if we started at s, then we wouldn't know which is the optimal path to t, and must explore a wide variety of paths, which is more time consuming, especially if the graph had much more edges and nodes. So let's apply the algorithm to the network and determine the shortest path. So taking a look at it, if we start off at t, what we have is the distance from t to itself is 0. So we can see we have our option of 0 there. Now, at every state, we'll have to make a decision which one is the most optimal to us. Now, at t, it's nice and simple because we've only one thing to choose from. So we have a value of 0. We've nothing else to choose from. So the decision is made for us. So the optimal choice at t is a value of 0. So now we move back a stage to g and h. At g, the distance from g to t, which we can see here, is 0 plus 20. So that'll give us a value at g of 20. And we have a little subscript next to it to show where we came from. So, and that's handy then for tracking our shortest path later on when we've everything completed. So we're not trying to figure out where we came from and everything. So it's a nice way to just keep track of things. So at G, we've only one option. So our decision is made for us. So our optimal choice at G is a value of 20. So, and then at H then, we have 0 plus 24 is 24 coming from T. So we'll have a value of 24 at H. And we've only one option there again. So our optimal choice is 24. So our decision is made for us again. Now, as we move back through the stages, so we have G and H completed. So we now move back and we're going to examine our next stage, which is D, E, and F. Now at D, we have two actions. So that connecting it to G and to H. So from G, we'll have a value of 20 plus 18 will give us a value of 38 coming from G. And we have from H then, we'll have 24 plus 17 will give us a value of 41 connecting it to H. Now we do have to make a decision. So we have a choice here to make. So we have to choose between 38 and 41. Our goal is to minimize costs. So in this case, we're looking for the smallest value. So our choice will be a value of 38, and that'll be our optimal choice at D. At E, we'll have, E is connected to G and E is connected to H. So for G, we have 20 plus 15 will give us an option of 35 connecting it to G. And for H, we have a value of 24 plus 14 will give us a value of 38 connecting it to H. So our smallest value there. So at every one of these states, we're making a decision. So, and we always want to choose the optimal one, which is our smallest for this context. So that's 35 connecting it to G. And at F, we have a choice of 20 plus 16 connecting it to G, will give us a value of 36. And for H, we have 24 plus 16, give us an option of 40 connecting it to H. Our smallest value is 36. So you can see our optimal choice there is 36. So we keep applying the same algorithm all the way through. And at this stage, we might say to our own students, if we're doing a class, we'll say, look, we're going to repeat this algorithm all the way through. So we might say, look, you finished from here, and we'll touch base then afterwards. So it might be a nice opportunity for them to see the first half of it and then to finish it, get stuck in and practice it. So, and we'll continue it from here then. So we move on to our next stage where we'll look at A, B, and C. So at A, we'll have 38 plus 22 connecting it to D, give us an option of 60. And connecting it to E then, we'll have 35 plus 26, giving us a value of 61 connecting it to E. 60 is our smallest number, so that's our optimal choice there. For B, we have three actions from B. So we'll have, for D, we'll have 38 plus 27, give us an option of 35. For E, we'll have 35 plus 28, give us an option of 63, connecting it to E. And for F, we'll have 36 plus 21, giving an option of 57. Our goal is the smallest one, so our optimal choice here will be 57, connecting it to F. And for C, we'll have 35 and 23 will give us 58, connecting it to E. And for F, we'll have 36 plus 24, give us an option of 60. Our smaller number is 58, so we're giving us an optimal value there at C. So we're nearly there, we've one left to do, and we're looking at S. And at S then, we have 3 actions connecting S to A, B, and C. So for A, we'll have 60 plus 28, will give us an option of 88. For B, we'll have 57 plus 27, give us 84. And for C, we'll have 58 plus 30, giving us a value of 88. Our goal is to choose the smallest one, and this will give us our final total cost over the 4-year period. So we'll have a value of 84. Now, all of our weights are represented in thousands of euro. So that gives a total of 84,000 euro of a cost over a 4-year period. And we also then want to know, right, what's our shortest path? So all of these actions could be various things in terms of, say, upgrades and maintenance, but we want to know what path should we take. So we have 84 came from B. So we'll have S to B. We'll have at B then, it was 57, F. So that's B to F then. At F, it was 36G, connecting it to G, and G was 20T, bringing us back to T, giving us a shortest path as outlined in our network here. So our total cost will be value for the 4 years of 84,000 euro. Our shortest path, which we just identified, was S, B, F, G, and T. And if we wanted to find out our average cost over a 4-year period, then that would be 84,000 divided by 4, giving us a value of 21,000 euro per year. So that'd be our average yearly cost. So from there then, we've applied Bellman's principle of optimality to our network, worked it through different stages in this multi-stage graph. And we now want to take a look at, right, from a modeling perspective, how could we look at our 4th stage of the modeling cycle, which is evaluating solutions? So in that, the final stage of the modeling cycle requires evaluating our solutions. So this involves refining the model and using it to predict a better solution to the problem. So it's an iterative process that leads to a more accurate solution. This could be built into any lesson where you might spend some time encouraging students to think about the accuracy of a solution based on any assumptions that were made and asking them to think about how their model could be refined. So maybe small stages that might focus on a particular stage of the modeling cycle every so often can really develop students' modeling skills. And with that, in this stage of evaluating solutions, students can also compare their solutions to solutions they might have found in, whether it be research that they might have done online or something that they might have found from real world data as well. So whatever the problem lends itself to. From there, having gone through the previous problem, we might compare and contrast Bellman's principle of optimality and Dijkstra's algorithm. In Leaving Certificate Applied Maths, they are both used to find the shortest path, but Dijkstra's is used in both undirected and directed networks, while Bellman's is used in a multi-stage directed graph like what we saw a moment ago. Dijkstra's can be used in graphs that aren't in distinct stages. Dijkstra's algorithm is a greedy algorithm which builds up a solution piece by piece, always choosing the next piece that offers the most obvious and immediate benefit. And Bellman's uses dynamic programming, which is an algorithm that helps to solve a class of problems that have overlapping subproblems through optimization. And finally then, Dijkstra's may not work if there is a negative edge weight, while Bellman's will work if there are negative edge weights involved. Dijkstra's algorithm will fail if a negative edge weight will produce a lower value at a node than the permanent value that has been already applied by the algorithm. So this brings us to an end of the section on algorithms, and we'll now take a look at the resources available on the PDST website, so where you might catch up on materials that might be helpful in the classroom. So if you're looking for information and resources that may be of use for you and your students in teaching and learning about applied maths, so if you go to the applied maths section of the PDST website, then you will find news about either upcoming events or maybe release material, whatever it might be, or up-to-date information on things like the SEC sample brief, or their information note regarding the project work of other new specifications. The information note offers a great insight into other new specifications that have recently added or maybe renewed a project component, and it gives good feedback on say a recommended best practice for students engaging with project work. You'll see on the right hand side of the page that we can see over here that there's an option for CPD resources, And if you click on that, then it'll bring you to all resources available. So on this page, you'll find videos regarding different parts of the course, which we can see up here. So you'll see digital graphic organizers that you or your students might find helpful for organizing learning. You'll find slides, booklets, and posters from all of our seminars and other events to date. So you'll also see the student modeling journal, so which we can see down here. So, and that everybody say that people would have seen in previous seminars, and this might be a helpful resource for developing your students' modeling skills and giving them a bit more independence in their learning. So you'll see you could download one, a PDF version if they might like to share with students. There's also an editable version so that students can actually type into the PDF. So whatever works best for you. So we also have larger versions of the posters that we gave out at the recent face-to-face National Seminar 5. And we'll also bring more to the next National Seminar 6 if anybody missed them. So you'll also find the Excel planning tool on the site, which you may find helpful in order for planning for teaching, learning, and assessment, or to keep track of what students have engaged with so far in their learning with applied maths. So if you have any thoughts or suggestions from today, or in general, then feel free to email us on appliedmaths@pdsd.ie. You can also follow us on Twitter @PDST Applied Math. Finally, we'd just like to say a huge thanks very much to everyone for attending today. So we know it's at the latter end of the year after school, it can always be a challenge to get to these things. So we really appreciate you taking your time to attend, and we hope you found it helpful. We hope you found it interesting, and that it might have a few ideas for students, or even that you might like to share with your own students going forward. Like Stephen mentioned earlier at the beginning, so we'd like to say a big thanks to everyone for all of your support over the past 2 years. And we're looking forward to another year next year of a few more events. So on that note, just to say thanks very much for this event. And we wish you all the very best going forward. And we hope you have a very enjoyable summer break. Thanks.